We've been talking about various cells here that you find as the formed elements within the formed element region marked here and the Buffy code as well. But let's actually name and describe each type and discuss their functions. Before we do, let's remember that the formed elements come from the lower portion of our blood sample here. And what we should note is that there are a variety of cells, and we're going to take a look at them here. Before we get into each of the individual type of cells, though, what we'll look at is that all of these cells ultimately come from blood stem cells. These stem cells are found within the red bone marrow of long bones. Stem cells ultimately are cells that have not differentiated. They can form any of the cells that need to be formed, in this case, any of the blood cells. What the stem cell will do when we need the various blood cells is it will divide and divide and divide and then start to actually differentiate into the various cells. So we have proerythroblasts, myeloblasts, lymphoblasts, monoblasts, and megakaryoblast. I list these out really quick here because you don't actually need to remember the terms for them. But what we can notice is that they all have the ending blast, which usually means building. These are ultimately the cells that are going to be built into the cells we have as formed elements. So the proerythroblasts become erythrocytes, red blood cells. The megakaryoblast forms platelets or thrombocytes. The myeloblasts become progranulocytes and then differentiate even further into basophils, neutrophils, and eosinophils. Lymphoblasts become lymphocytes, and monoblasts become monocytes. These types of cells in the middle are all white blood cells. Here we have the granulocytes, the basophils, eosinophils, and neutrophils. They're called granulocytes because the term cytes means cell, and granulo is referring to the grains that you see within the cytoplasm. When people were first investigating these and using microscopes to look at them, they noticed, hey, there's all these little dots within the cell, and so they called them granulocytes. They differ from the lymphocytes and the monocytes because, as you can see, they have no granules within their cytoplasm. So these are called agranulocytes, the prefix A meaning no. And so if we were to translate the term agranulocyte, it means no granules in the cells. Ultimately, as I mentioned, these are all white blood cells, or leukocytes. I will mention here that you should get used to the terminology for each of these cells. In terms of red blood cells are erythrocytes, white blood cells are leukocytes, and platelets are thrombocytes, because both terms are used within your professions. We will also need to know the subcategories of granulocytes and agranulocytes, and then the subcategories of the cells within those two categories. Let's take a closer look then at each of these types of cells. Here's a red blood cell, an erythrocyte. What you'll notice about this cell is that it is biconcave in structure. Biconcave refers to bi meaning two, and concave meaning indented. And so both sides, the two sides of the red blood cell, are actually indented. The reason for this is that a red blood cell does not have a nucleus. The reason for this shape is that it allows a normal red blood cell to be very flexible. The capillaries that we'll take a look at later in the course when we look at blood vessels are actually only one red blood cell wide. The capillaries are where gas exchange and nutrient exchange occur with the blood and the surrounding tissue. Because they're only one blood cell wide, it's good that the erythrocytes are flexible because, as you can see in this picture, they're sometimes bumping around or being forced through, and they need to be flexible so they're not getting damaged. Part of the reason that the red blood cells don't have a nucleus is that ultimately they're filled with hemoglobin. In my oversimplified way of thinking about it, I think a red blood cell is basically just a bag of hemoglobin. There are approximately 250 million hemoglobin molecules within one single red blood cell. Hemoglobin is a molecule that looks like this. It's made up of the globulin group, the purple group shown here, but what that ultimately is proteins, and there are 4 protein subunits that are formed via transcription and translation and then combined together to form the hemoglobin. And then in the middle of each globin portion, each protein portion, you can see a heme group. It's indicated here just in yellow because ultimately what it is a large complex molecule, and we don't need to know the structure of it. But within the middle of that heme group is an iron atom. And so as you can tell from the picture here, we have 4 globin or protein parts that come together, each with a heme group within the middle, each with an iron atom within the middle of the heme group. So ultimately, one hemoglobin has 4 iron within it. The iron is actually the region that the oxygen is going to bind to for transportation throughout the blood. Therefore, each hemoglobin molecule can actually hold 4 oxygen molecules. In one red blood cell, we have 250 hemoglobin molecules. If each can carry 4 oxygen molecules, then each red blood cell can carry approximately 1 billion oxygen molecules. And in the end, this is the function of red blood cells, to have all this hemoglobin because ultimately they're going to transport oxygen around the body. Therefore, one thing we should note is that oxygen levels are going to affect how much red blood cells we actually have. When we have a decrease in oxygen levels within our body, for whatever reason, it could be that you moved into the mountains and you're now at a higher altitude and therefore there's less oxygen within the atmosphere at that region. But whatever the reason, if we have a decrease in the amount of oxygen in our body wants to maintain homeostasis. And so how it can maintain homeostasis and increase the amount of oxygen being transported in our body is to produce more red blood cells. How we do that is a multi-step process. The first step is that as the oxygen levels in our body decrease, it's actually our kidneys that recognize that. We haven't got to the urinary system yet, but earlier I was mentioning that lots of blood goes to the kidneys in order to be filtered. So as that blood travels through the kidney can monitor the amount of oxygen within the blood. If the oxygen levels dip, then the kidney will release the hormone erythropoietin. That hormone will travel around in the blood going to our red bone marrow. The red bone marrow of our skeletal system is actually involved in making all of the blood cells that we've looked at so far, the red, white, and platelets. When the erythropoietin arrives at the red bone marrow, it triggers the production of red blood cells. We have an increase in the amount of red blood cells. They move into our cardiovascular system, and because there are more red blood cells, we can now transport more oxygen, and we've maintained homeostatic levels of the amount of oxygen within our body. As I mentioned, you might move to the mountains to a higher altitude where there's less oxygen. At first it will be hard to breathe, but after a few weeks, what will happen is this process will have increased the amount of red blood cells within your blood, and you will better be able to transport the oxygen. And so you'll find that over those few weeks, it will be a lot easier to breathe. Just to make a connection here, we can talk about how athletes actually use this to their advantage sometimes. So athletes that are involved in long-distance sports, running or biking, what they sometimes do is move to somewhere at high altitude and train for a few months before a competition. The reason is that as they train, but they're in lower atmospheric oxygen levels, their body will respond in this way. Their kidneys will release erythropoietin, causing their red bone marrow to make more red blood cells, and increasing the amount of oxygen that they can actually transport. But then when the competition happens, if the competition is, let's say, at sea level, then this athlete now has a lot of red blood cells, more so than they need at sea level, but they're much more efficient at transporting oxygen. Even though I'm using this competition example, we all undergo this process. Because our red blood cells, not having nuclei, or very many organelles in fact, do not last very long in our bodies. The average lifespan of a red blood cell is actually only 120 days. Since every month is approximately 30 days, that's on average that your red blood cell lasts only 4 months before it's too old. What happens when those red blood cells then are too old? As our red blood cells get older and older, we want to actually recycle the materials that make up the red blood cell, ultimately the hemoglobin. As we've already mentioned, the hemoglobin is made up of two parts, the protein, globin, and then the heme group with the iron in the middle. We don't want the red blood cells to break down and then our body just excretes all of these materials as waste. And so what happens is that the globin, the protein, is broken down into the amino acids that made it up. In the end, those amino acids can then be used to produce proteins in the rest of our body or in producing more red blood cells. The heme group can be broken down such that the iron becomes stored within the liver. And in that way, it can then be recycled as our red bone marrow makes more red blood cells. The iron can move to the red bone marrow, and we can reuse that iron in new red blood cells. The heme group is actually the only item that we break down and get rid of. The heme group ultimately becomes part of bile, which our livers make and then secretes into our intestines in order to be excreted later as waste. As previously mentioned, white blood cells, or leukocytes, are cells that are involved in our immune response. They're large round cells that do contain nuclei, unlike red blood cells. They protect the body by destroying disease-producing microorganisms called pathogens and removing old dead tissue. They do this in a variety of ways. So let's take a look at the various types of white blood cells. The first we'll look at are the neutrophils. The neutrophils are the most common type of granulocyte. Neutrophils get their name because when stained using chemicals in order to better see them under the microscope, they do not stain any particular color, and so they are neutral. The neutrophil's most important role is phagocytosis. These cells are very common and remain in the blood for about 10 to 12 hours, and they move around the body and phagocytize any pathogens that get into the body or any old and dead tissue. A second type of granulocyte is called the basophil. It's present normally in small numbers, and it gets its name because when stained for microscopic imaging, it reacts with a specific basic solution and turns the color blue. The basophil plays an important role in the inflammatory response that we'll take a closer look at when we get to the immune and lymphatic systems. It plays the inflammatory response by releasing the chemical histamine. It also releases the chemical heparin that acts as an anticoagulant. Eosinophils are the third type of granulocyte. The prefix eos means red, and it comes from the fact that when stained for microscopic viewing, it reacts with chemicals that are acidic and it turns red. Eosinophils are also involved in inflammatory response, secreting chemicals that destroy certain parasites when they get into the body. There are two types of agranulocytes, as we mentioned earlier. The monocytes, like the neutrophils, are involved in phagocytosis. The neutrophils are more abundant than the monocytes, but the monocytes are more efficient phagocytes. As monocytes differentiate, they turn into macrophages. The term macrophage comes from the terms macro meaning large and phage meaning phagocytosis. And so these are large eaters that move around the body and they will attack and phagocytize dead tissues or pathogens that have got into the body. The lymphocytes play an important role in immunity and form T cells and B cells. We'll take a closer look at T cells and B cells when we get to immunity later on in the course. So now that we've looked at a basic overview of what all these cells do, we can look at how they move within the blood. Unlike red blood cells that move within the blood vessels and stay within the blood vessels, white blood cells can actually move out of the blood vessels into surrounding tissue. When they move into the surrounding tissue, they might come across injured cells or pathogens that ought not to be in the body. And then, as we mentioned, neutrophils and the monocytes that become macrophages will undergo phagocytosis. What they will do is actually envelop or wrap around the pathogens or injured cells and take them into the cell, into vesicles, and then we'll use digestive enzymes to break down those pathogens or injured cells. The other cells that we mentioned are not involved in phagocytosis, but are involved in cleaning up the pathogens and dead cells via releasing the chemicals that we mentioned as we went through each type of cell. So now that we've talked about white blood cells, or leukocytes, let's move on to the third and final formed element in the blood. The megakaryoblast, as we mentioned earlier in this unit, will form ultimately platelets, or thrombocytes. The thrombocytes are involved in blood clotting. So let's focus in on just these cells. When we get a cut, what happens is that the blood vessels within our tissue will start to spasm. Of course, red blood cells and white blood cells as well will be coming out of the blood vessel in that area. But then as the blood vessel spasms, the platelets will come into the damaged area and form a platelet plug. The platelet plug is, as the name sounds, a plug where there's a whole bunch of collection of platelets and they sort of form a jam in that area, or they jam up the hole. But this is not the full clot at this point. As the platelets go into that area, they actually form the clot by causing a number of reactions that ultimately form fibrin threads. Fibrin is a protein that helps to catch red blood cells as well as the platelets and causes them to form a clot in the area of the damage. So how do these fibrin threads get formed after the platelets form the plug? Hemostasis involves 3 steps. Hemostasis is the formation of a blood clot in order to maintain the integrity of a blood vessel. It sounds like homeostasis, but homeostasis is a more generic term, just saying stability of the body overall. Hemostasis is referring to stability of the blood and the blood vessels. The 3 steps involved are: the blood vessel is damaged, and then as cells are going out, prothrombin activator starts to be released from platelets that start to form the plug. The prothrombin activator causes stage 2, which is prothrombin, which is normally floating around in your blood but is an inactive form of the protein, gets converted into thrombin. Prothrombin activator, in order to function in converting prothrombin to thrombin, also needs calcium to be involved. After prothrombin is converted into the active form thrombin, the thrombin reacts with fibrinogen, which again is, under normal conditions, moving around in your blood but is inactive. And the thrombin converts the fibrinogen into the active fibrin fibers that then trap red blood cells and ultimately form the blood clot in the area of the damage. So what happens over time as the tissue that has been damaged is ultimately repaired? Let's take a closer look at that blood clot. After the tissue has started to repair itself, fibrin starts to degrade. How that happens is we have the inactive protein plasminogen, which becomes activated, forming plasmin in our blood, and it moves around the blood and degrades the fibrin and releases the old red blood cells that were trapped within the fibrin.